Hello there, valued viewers and valued students. Welcome to the first recap of a lecture that was given at around 12:30 p.m. EST today. This was actually our first lecture of the entire custom flight combat program that you will be taking over the course of the next couple of weeks. And I'm happy to inform you that our first lecture went very, very well. Now, down to the point. You guys are here because either you want extra info, you didn't understand something, or you just missed a lecture. Now, it's highly recommended that you attend these lectures when they happen. However, I completely understand that many of you have extenuating circumstances, say time zone issues, family, friends, school, life stuff. I mean, there are things that are way more important than Roblox. So please just don't jeopardize your life, school, or social life for that matter for a air combat simulator video game. Now, even though I'm teaching you a lot of stuff that applies to real life, like real physics and real combat tactics and real BFM, there are certain things that, while great knowledge, it is, I guess you can call it, while these things are just great knowledge to have and great things to learn, especially if you're going into a career with some sort of aviation in mind, or if you just want this knowledge in general because you want to be a better pilot. There are just things in life that are more important. So please don't let this interfere with anything else that you're doing. Anyways, now down to the point. Today we're going to be recapping, or I guess learning for those of you who aren't there, the basics of flight. So we're going to go into flight physics, how things fly, what lift is, what angle of attack is, how things don't fly, so how stalls work and how to avoid it, what a stall looks like, and basically just the general mechanics of flight and how it works. As you can see, I'll give you a quick preview of the slides we're going to be going over. But yeah, and we will go into a little bit of turning. Now, in a later video, the one probably after this, we will talk about how to fly the system. If you were in class today, you'll already know how to fly the system. However, if you weren't, there will be a follow-up video to this, which will show you the controls, how to start up the plane, how to fly, uh, general basics, things like that. And everything should be understandable as long as you understood everything in this video. The videos are supposed to supersede each other, so you should watch them in order. I won't post something that we haven't learned yet without giving you something beforehand that you'll need for it. Anyways, and then the video after the second one will be the fun stuff, BFM, dogfighting, things like that. But we'll get there eventually. This is among the more boring video, and as the course goes on, I'd also like to let you know that the lectures will get less and less, and there'll be more in-game time to fight. All right, we're going to do a lot of dogfighting practice in game. And as the course goes on, after I teach you um, different scenarios and things like that, and more specifically, different situations you might find yourself in, like a rolling scissor, a flat scissor, or a rate fight where you're defensive or offensive or something of that sort. After I teach you certain maneuvers to counter and do things like that, or how to get out of a certain situation or win a certain situation, after we go through all that, the rest of the lectures and classes after that will basically just be us dogfighting. And by us, I mean the class versus the class and me versus a few of you guys. And we'll record those videos and we'll break them down and see what you did well, see what you did wrong, because all of you are going to have different strengths and weaknesses, and we want to play to those strengths and weaknesses, specifically the strengths. We want to avoid the weaknesses and correct them. But, anyways, all right, on to the video. So, basics of flight. So, on any aircraft, there are four forces that are acting upon it at any given moment. Okay, and we represent these with vectors. A vector is just basically a line that we'll use that has both direction and magnitude that is going to represent a force in this case. The longer the line, the more force is there. The smaller the line, the less force is there. So in this example, the thing that you have in front of you, we have an aircraft in flight that is accelerating. Okay? But anyways, I'll talk about why it's accelerating. And before I do that, I'll explain the four forces. So, force number one is lift. All right, lift is the force that keeps the aircraft in the air. Then we have drag. Drag is something inevitable that all things have. Okay, aircraft have drag. A paper plane getting thrown through the air has drag. If you throw a book through the air, it has drag. Anything going through air or fluid, for that matter, has drag. Um, And planes are very aerodynamic, so they try to reduce the amount of drag, right? So think about drag like this: if we had a piece of paper and we blew on it, right? If we blew on this piece of paper, if we blew air at it, um, that'd be a lot of drag, right? And it would get pushed back. But say if we held the paper sideways and we blew on it, it wouldn't get pushed back as much. There's a lot less drag. It's very thin now, right? We would have less drag, and that's because it's a little more aerodynamic if it's laid flat. But anyways, that's a little thing about drag there. A little info about that. Anyways, then we have weight and gravity. So weight and gravity are interchangeable. It's really weight or gravity. You can call this force weight. You can call it gravity. They both work. This is not weight divided by gravity. This is just weight or gravity. So weight slash gravity. And that's the force, obviously, that brings the aircraft towards the earth or towards the ground. And then we have probably the second most important besides lift, thrust. Thrust is actually what allows your aircraft to move forward. You would get nowhere without thrust. Thrust is obviously created by the engines. So this aircraft in this image is accelerating here because the thrust vector, this line that represents thrust, is much, much longer than the drag vector. It's exceeding it, and therefore this aircraft is currently accelerating in forward flight. Now, some of you might be thinking, what's this down here? Well, that's relative wind. Relative wind is essentially a force that acts opposite to the aircraft. Relative wind is not really a force per se. I said force, and that's my mistake there. It's more of just a consequence of flight, really. Relative wind just represents the direction that the airflow is hitting the aircraft from. So the direction that the wind is hitting the aircraft. Relative wind will always hit the aircraft from its actual position, like the way it's moving. If the aircraft is moving this way, relative wind is going to hit it in the opposite direction that way. You know, if you, for example, were running forward, the relative wind is going to hit you forward. You know, the wind in your face. If the aircraft was moving straight up, then the relative wind would be straight down. Okay, it's basically just where the aircraft is moving. It's not always where the nose is pointing. Um, it's quite literally where the aircraft is moving, right? So, anyways, those are the four forces that act upon an aircraft. Relative wind, we'll talk about it more later. So, how does an aircraft stay in the air? Well, an aircraft stays in the air because of something called an airfoil. An airfoil is a shape that's very good at generating lift. Now, anything moving through a fluid can generate lift or has the potential to generate lift. A car, for example, generates lift, especially really fast cars like sports cars and race cars. They generate a lot of lift. That's actually why spoilers exist. Spoilers exist to spoil the airflow, that's why they're called spoilers, and decrease the amount of lift that the car faces. By decreasing the amount of lift, the car gets more traction because it stays on the ground more, right? I mean, that's why cars don't take off. Cars can't take off. They don't produce that. They don't produce enough lift to take off. Um, but anyways, so what does produce enough lift to take off? Well, let's look at a paper plane, for example. A paper plane is light, and it produces enough lift to take off. Its wing is like a rectangle like this. All right, that's a very, very crappily drawn rectangle, but I'm no artist. But anyways, in a rectangle, if we were to draw the airflow over this, it would look something like this. There we go. It would look something like that. But basically, what we see here and the reason this is generating lift is because air is being directed downward. And when air is being directed downward or a fluid is being directed downward, the equal and opposite reaction is for something to move up, right? That's Newton's law. And in this case, air is being directed downward. This fluid is being directed downward. And so something has to move up, and that's going to be our little paper wing there. However, that's all fine and dandy. That's one way lift is generated. But airfoils are a shape that's just really, really good at generating lift because it also directs air downward, but it does something else, something a little more important, or not really more important, equally as important, I'd say. And that is it uses pressure along with directing air downward. So it uses Newton's third law in something we call Bernoulli's principle, which is where the pressure comes in. So let's talk about Bernoulli's principle real quick, and I'll give you it in the simplest form I can. Say we have, I don't know, a pond with a river in between or a lake in between, and then another pond. If we have a bunch of water here, right, and the water's flowing this way, it gets into the narrow part of the river, and then it kind of goes back into the other pond. Where would water be moving the fastest? Is it going to move faster in the narrow part or faster in the wider part? Well, the answer is it's going to move faster in the narrow part. Okay, when a fluid gets compressed, the velocity of that fluid speeds up. Like, and if it's moving, all right, if it gets squeezed together, it's going to speed up. And when a fluid does not get compressed and it has space to expand or flow, then it's going to decrease in velocity. And Bernoulli's principle tells us that when the velocity increases, the pressure decreases. And when the velocity decreases, the pressure increases. So why does this matter? Well, let's look at our airfoil here. The airfoil is a shape that's very good at kind of pushing and squeezing air together over the top of the wing and not doing so over the bottom of the wing. So here's our chord line. It's basically a line right here that it's an imaginary line that connects the front of the airfoil, the frontmost point, to the backmost point. Okay, it's an imaginary line. And that chord line kind of just tells us where it's facing, like the direction it's facing. The chord line of an airfoil on an aircraft would also basically be just where the aircraft is pointing, right? Because your wings are aligned with your aircraft for obvious reasons. Um, anyways, so look at the airflow here. Similar to our river example, we see how air gets kind of pushed together over the top of the wing up here. And we see how it's kind of very separated down here. It's not very condensed. And we saw that if a fluid is kind of condensed like this, it's going to speed up in velocity. And if it speeds up in velocity, it has a low pressure. And the opposite is true for the bottom. It decreases velocity and it has a high pressure. That's why air over the top of the wing reaches the back of the wing faster. Basically, air moving over the top goes faster, creating lower pressure. And then, of course, we have the same old air being directed downward thing here. We have air being directed downward by the top of the airfoil. And that also contributes to lift. That's Newton's law again. So basically, it's a shape that's really good at generating lift. Okay, it's much better than a paper airplane wing. I mean, come on. Jets use it for a reason. Fighter jets use it for a reason. In fact, all airplanes do for that matter. But anyways, relative wind, airfoil, low pressure, high pressure. That's the basics of flight. There's really not much else to it as to how lift is generated. This is obviously very simplified, but you don't need to know more than this. So how does that apply to our F-15 here that we're learning and training in? Well, this is an F-15. This is the wing here. It's the airfoil. Horribly outlined, but that's your airfoil. And the same thing applies. Low pressure, high pressure, air being directed downward, thus tons and tons of lift. I don't know why I curved that line. That's not lift at all. That's lift. Okay, so that's how lift is generated. Now let's get into some important stuff. So what I'm going to do here is I'm going to open up a file. I'm going to try and find the file for you guys. Let's see. This one. Nope, we did this. Did that. That's just blank. Here we go. All right. So now we're going to start talking about angle of attack. Okay. We saw how lift was generated, and now we need to talk about angle of attack. Okay. So here's the entire F-15, but all that really matters is the airfoil. But anyways, let's look at this. So this black line is the actual direction of travel. Here we have two aircraft traveling at different speeds. We have one that's slow and one that's pretty fast. Um, and essentially, this guy's real slow. Okay, so his nose is pointed up, but he's so slow he cannot climb. So he cannot travel up because he's too slow to do so. And so his actual direction of travel is forward. Okay, he's fast enough to pitch his nose up and hold it there, but he's not fast enough to actually climb. So he's going to continue to travel forward. And we said that relative wind hits you from the direction of travel. And so relative wind will hit him here. This guy, however, is fast enough to climb. So relative wind will hit him head on. So why does this matter? Well, the angle of attack is basically the angle of the airfoil in relation to the relative wind, or better said, it's the angle of the chord line, the way the airfoil is facing, in relation to the relative wind. So if we look here, this is a very high angle of attack. This is our angle here. Okay, so this is angle A. Angle A is also referred to as angle alpha. But let's imagine this is, I don't know, 27 degrees angle of attack here, right? At 27 degrees angle of attack, you're not going to get that much thrust. Well, you can apply thrust here, but you're going to get a lot of drag because now there's a much larger surface of the wing being hit. So it's going to be hard to accelerate at high angles of attack. You lose speed at high angles of attack generally. You're going to generate quite a bit of lift because you're going to need that to stay in the air now that the drag's increased, and your weight's going to stay the same. And then we have when you're fast enough, right? When you're fast enough to climb, and this is not necessarily a stall. This is just you can't climb. A stall is if he was like 420 maybe. At 420, I have a feeling he would stall. And we'll talk about what stalling looks like on an airfoil in a second. But anyways, now moving on to this guy. This guy has enough of speed to be able to climb, so his actual direction of travel is here, and he's aligned with his lift vector, and the relative wind is hitting him from the front, and so it's really no different than this. This and this are basically the same. When we talk about stalls, so stalling happens when you're, number one, too slow, and number two, when you exceed the critical angle of attack. What does that mean? Okay, so if your angle of attack is this much, ready? Let me draw two airfoils at different angles of attack. Let's draw one like that, and let's draw one at a really high angle of attack like this. We're going to pretend that the relative wind for both of these airfoils is coming from this direction. Okay, and we said the direction it's facing is the chord line, so from the back to the front, and here from the back to the front. So the angle of attack here is that much, and the angle of attack here is this much. This is a higher angle of attack. Why does that matter? All right, well, let's draw the airflow. Let's draw the airflow. Sorry, airflow over the airfoil. The airflow is going to look like this. A lot of air being pushed down. Still the same principle. Still condenser over the top. Still less condenser over the bottom. Still difference in pressures. A lot of air being pushed down. A lot of lift being generated. And at a high angle of attack, like this, in this particular scenario, you'll be fine. However, there is a point at which you can reach a too high angle of attack. All right, and if you reach too high of an angle of attack, we call that your critical angle of attack, and you will stall. All right, and this is a critical angle of attack, and the airflow would then look like this. And in this case, we have a lot of air being pushed down here, but not enough being pushed down here. And you'll notice there's a separation of the airflow from the airfoil. All right, at this angle, the air cannot stick to the airfoil, which means there can't be much of a difference in pressure and not enough air is being pushed down. And therefore, you will not generate enough lift to stay in the air and you will stall. And in between here, this is all just turbulent air. This is all just turbulent air. It's not helping you out much. It's not generating lift. This is very bad. This is what a stall would look like. And it happens when you reach too critical of an angle of attack and you're too slow. The reason I say if you're too slow is because if you're fast enough and you're at this angle of attack, you'll just climb. And your angle of attack will go back to zero because now the relative wind is up here. So you would never hit your critical angle. You can hit it very easily though if you're slow. So be wary of that. So now we know angle of attack is just the relation between where the airflow is facing and where the airflow is coming from. And I'll give you an example in Project Eagle of this. Let me grab this real quick. All right, let's fast forward here. Here we go. All right. This is a very, very high angle of attack. I am too slow to climb, so I'm not exactly climbing here. I will for a second, but now I'm too slow to climb. And since I'm too slow to climb, the direction of the relative wind cannot change. So my nose is pointed up, but I'm not going up. So even though my nose is pointed up and my airfoil is pointed up, my wing, right? Even though those things are pointed up, I'm not traveling upward. Look at my altitude. Watch here. It's decreasing. I'm stalling. I'm basically falling out of the sky, even though my nose is pointed up. So it's important to note that you will not always go and fly in the direction that your nose is pointed at different angles of attack. So even though my nose is pointed up and I can sustain it and keep it up, you can see the vortices coming off my wingtips and they're showing my true flight time. I'm actually just going straight, even though my nose is pointed up. So I'm not gaining anything. I'm not, and actually I'm kind of losing something because I'm losing altitude as I do this because I'm too slow. This is essentially a stall right here. You can see I'm flying straight, but my nose is pointed up and I'm not going up. Now, watch what happens. Oh, also, but real quick, it's important to note also the relative wind in the scenario. If it'll let me go back. There we go. The relative wind in this scenario. Great, it's not letting me go back. My bad here. Okay, the relative wind in this scenario is coming directly in front here, not where my nose is pointed. It's hitting my aircraft right here. We can see it by these lines. So the relative wind is coming from in front. And that's because I'm too slow and I'm not climbing, and because I'm not climbing, the relative wind is not coming from where I'm actually, it's not going from where my nose is pointed. It's going from where my aircraft is actually going. Remember, we said earlier that I'm actually going straight even though my nose is pointed up. So if I want to fix this, how am I going to fix this? Well, I'm going to add power. What I'm going to do in a second here is I'm going to kick in the afterburners. And by doing so, I'm going to build enough speed to climb. Also, on the HUD here, this is your angle of attack indicator, this number here. Right now I'm at 29 angle of attack, which is honestly ridiculous. I shouldn't be doing that. This is just for demonstration purposes. But now I'm at 29.2. That's your angle of attack indicator. So that's going to help you out, kind of figure out what angle of attack you are at. And it's going to hopefully help you avoid a stall. But anyway, so how do I fix this? Well, I'm going to add power in a second here. All right, so there we go. Burners now. And as you can see, I'm gaining speed, and now because I'm gaining speed, the direction of the relative wind will change. Now I'm actually climbing. I'm gaining altitude. And you can see the vortices kind of go away. And now I'm fully climbing. I'm at a good speed to climb. And now the relative wind is no longer coming from in front here. It's coming from where my nose is pointed. And now I'm actually going where my nose is pointed because I have the speed to do so. So that's just something that you need to keep in mind. And of course, once I'm climbing, the angle of attack indicator now goes back down to about 0, which is, whenever you're traveling in the same direction that your nose is pointed, your angle of attack is low. If you're not traveling in the direction that your nose is pointed, for whatever reason, whether it be speed or angle of attack or you're pulling too hard, your angle of attack is going to increase. And if you increase it too much, you will stall. That's the basics of the physics of flight. That's honestly really all we need to cover for this one little video here. John and Spec already did this on Sunday, so he's here for a review, and John is learning this just now. But that's the basics to flight and what angle of attack is. So hopefully by the end of this video, you should know what angle of attack is, and you should know how planes stay in the air. All right, because if you're going to become fighter pilots here and you're going to train, you should at least know how a plane works. It'd be kind of embarrassing if someone goes up to you and says, "Oh, look at you! You're in that Roblox flight program. Cool. How does a plane work?" And you don't know the answer. That'll be sad. I really do not want that to happen to one of you, because that'll look bad on me, considering I'm your instructor. So, by the end of this video, you should know what angle of attack is, and you should know how planes fly and how lift is generated and how they work.